Harry Potter is one of my favorite movie series. Every fan knows that in order to get to platform 9 3/4 at London's King's Cross station, you have to get through a barrier. What if I told you that this kind of magic is permissible in quantum mechanics? What if I told you that when you were upset and banged your fist or head against a wall, there was a non-zero chance that your head or fist could go straight through that wall to the other side? Now, the caveat is that for macro objects like your fist or body to go through a wall, the probability is extremely low. But this probability rises appreciably as you get to smaller and smaller objects. So much so that by the time you get to fundamental particles like electrons, this tunneling effect can take place all the time. In fact, quantum tunneling is responsible for life on Earth because without it, the sun would not shine. It also plays a critical role in our efforts to build ever more powerful computers. And quantum tunneling could even be responsible for the very existence of the universe. It may have caused the Big Bang, which occurred 13.8 billion years ago. What is this mysterious quantum tunneling effect? Where does it come from? And why is it one of the most important phenomena in physics? The explanation is coming up right after this. Before I get into the unbelievable explanation of quantum tunneling, let me say a word about what inspired me to create this video. I saw a documentary on Magellan TV, today's sponsor, called Seeing Inside the Sun. It uses some incredible supercomputer graphics to show the fluid dynamics inside the sun. This got me thinking about how the fusion process actually works. Magellan is an ad-free documentary streaming service created by the filmmakers themselves. Their collections are richer and broader than anything else you'll find. You can dive deep into subjects like history, culture, science, and technology, many in 4K. I'm delighted to tell you that Magellan has a special offer for Arvin Ash viewers right now. If you click on the link in the description, you'll get a free 1-month trial. Make it a New Year resolution to treat yourself to these great documentaries. Be sure to click the link in the description. Imagine that you have a tennis ball rolling back and forth in a frictionless box. When the ball hits the side of the box, it just bounces back and forth. The only way for the ball to get on the other side of the box is either to gain enough energy to go over the wall by perhaps you picking it up and putting it on the other side, or by having enough energy to break through the wall. There's no other way in classical physics. What if instead of a tennis ball, this was a quantum object, like an electron? The rules of quantum mechanics are such that quantum objects have a wave-particle duality. This means that what we think of as an electron particle actually behaves like a wave, a probability wave. This means that its position is not a precise location in space. It is defined by a wave function that can only tell us the probability of finding it at a particular location. And while you may think it is in the box in front of you, the wave equation is such that there's a non-zero probability that the electron can be outside the wall. In fact, quantum mechanics shows that the wave function of a particle exists in all of space, in the entire universe, up to infinity. So the astounding revelation of quantum mechanics is that while you think this electron is in the box in front of you, there's a non-zero probability that it could be on Mars. The chance is very, very, very small, but the important thing is that this probability is non-zero. So what governs this kind of behavior? We can attribute it to the Heisenberg uncertainty principle. I would not say it is a cause, but rather a description of its behavior. Basically, this principle states that the uncertainty in a real particle's position times the uncertainty in its momentum has to be greater than a finite number. Practically, this means we cannot know with 100% certainty what the position of that electron is. And the wave function of the electron, which gives us the probability of finding it at any location, can be found using the Schrödinger equation. So let's take a closer look at that and figure out how it shows the probability of finding our electron outside the box. The Schrödinger equation was developed by Erwin Schrödinger around 1926, and it's the equation that describes the wave nature of matter. This is the time-independent form of the Schrödinger equation. The Greek letter psi in the equation is the wave function. Though the wave function depends on both time and position, we're going to look at only how it varies with the position to figure out how our electron will behave around a barrier. The wave function can be both positive or negative, but the square is always positive. And it so happens that the square of the wave function, which is a function of position x, gives us the probability of finding that particle in that position. The first part is the kinetic energy operator acting on the wave function. The second part is the potential energy operator acting on the wave function. After the equal sign, it is the total energy acting on the wave function. The Schrödinger equation is basically a statement of the conservation of energy. It says that the kinetic energy plus potential energy equals the total energy. But instead of just energies, we have the energy operators that are acting on the wave function of the particle. Let's now consider the case of a particle inside a box with a wall that has a finite thickness and finite height. We can solve for the wave function inside the box, but outside the barrier. And it will look something like this, where L equals the following. M is the mass, E is the total energy, C is the amplitude, and X is the location of the wave. This is a typical sinusoidal wave. We can also solve the wave function for inside the barrier. Psi 2, in this case, looks like this. V0 is the potential energy. What the mathematics of the wave function inside the barrier shows is that it decays exponentially. As x, the distance or thickness of the barrier, gets larger, the psi function becomes smaller, but it never reaches zero. This shows us that the function is non-zero in a finite wall. This means that our particle can end up on the other side of the wall, and we can solve for the wave function outside the wall, psi 3. In fact, psi 3 looks identical to the wave function inside the wall. The amplitude will just be much smaller. The amplitude indicates the probability, so the lower amplitude just means the probability of the particle being there is going to be lower. Now, like I said earlier, the square of the psi function gives us the probability of finding the particle there. So as long as the wave function is non-zero, there's a non-zero probability of finding the electron there. This is quantum tunneling. It represents the non-zero probability of finding a particle where classical energy conservation would prohibit it. So why doesn't this math work for large objects like a tennis ball or our bodies? If you look at the wave function, what you will find is that it depends on several factors. The thickness of the barrier, the height of the barrier, or V0, because that determines the potential energy required to overcome it, and the mass of the particle. For macro-sized objects like a tennis ball or your fist, the mass is so large and the thickness of the barrier is so great that the wave function will have an extremely small value, making the probability extremely small. In fact, if you do a rough calculation for my hand or my body to tunnel through the wall, the probability will be about 10 to the negative 40. More zeros than there are atoms in my body, which is about 10 to the 28. This is statistically impossible, though not physically impossible. So what are the chances that you can walk through a wall and get to platform 9 3/4? The answer is not zero. The thinner the wall and the shorter the wall is and the lighter the particle is, the higher the chance that it can overcome the energy required to tunnel through the barrier. By the way, when I say barrier, it doesn't necessarily mean just a physical barrier. It can be any energy barrier. Now, this tunneling effect has huge implications in nature and technology. For example, electronic devices are generally based on transistors. A transistor can be made in different ways, but they all have the same general form. There is a source on one side, a gate or barrier to control the flow of electrons to the drain on the other side. If we look at a transistor from the side, we essentially have the same situation as with the electron in a box. If the control gate becomes too small, the electrons just tunnel straight through, ruining our circuit. In fact, modern transistors are so small that tunneling becomes an issue. This is why you cannot make transistors any smaller. And this is a big roadblock for developing better, more powerful, more miniaturized electronic devices. In nature, quantum tunneling is responsible for the sun shining. How, you ask? Stars shine due to nuclear fusion. Fusion is when you take two light elements like hydrogen and fuse them together to make a heavier element, like helium. The process usually results in the release of excess energy. Hydrogen bombs also work similarly. The most abundant element in the universe is hydrogen, and this is also what the sun is mostly made of. It is its primary fuel source. The sun fuses the nuclei of hydrogen atoms together to form helium. Larger stars can produce atoms up to the size of iron using this same fusion process. Tunneling is essential here because hydrogen nuclei are composed of positively charged protons that repel each other. In order for them to come together, they have to overcome this extremely strong repulsion. This is called the Coulomb potential. In order for the sun to ignite, two hydrogen nuclei have to overcome this Coulomb potential in order for them to get close enough for the strong force to take over and fuse them together. This repulsion is an energy barrier. But because of quantum tunneling, the probability for this process to occur becomes much more likely because the two nuclei can tunnel through this barrier. It's like going on the other side of a mountain through a tunnel instead of over it. If it weren't for quantum tunneling, most stars may never have ignited. Although the hydrogen atoms fuse into helium, this helium can also start fusing into bigger atoms in bigger stars, where elements like carbon, oxygen, and nitrogen are formed. These are, of course, critical for life. The most remarkable effect of quantum tunneling is the possibility that the universe itself may have come to be because of it. The most accepted theory of the beginning is that the universe came from an infinitesimally small point called the singularity, where all the energy of the universe was initially located. It expanded exponentially through an inflationary process that overcame any attractive forces such as gravity. This is better known as the Big Bang. But the big mystery is, what gave the universe the kick that it needed in order to overcome the energy required to counteract attractive forces like gravity? This is not well understood and not proven, but according to calculations made by physicist Alexander Vilenkin, the probability that the universe could overcome the energy barrier needed for inflation to occur and the Big Bang to result is not zero, even at the limit of the universe being size zero, that is, having no space and no time. In other words, the Big Bang could come from nothing. If this is true, then the process of quantum tunneling, which comes directly from the most important concepts in quantum mechanics, is absolutely the most important natural process in the universe. And I hope this video helped you understand this astonishing property of nature a little bit better. I'd like to thank my generous supporters on Patreon. If you like my videos, consider joining them. I will see you in the next video, my friend.